So thank you everybody for coming. Thank you Marius and Giulio for the invitation. I really appreciate it. Hong Kong is beautiful, so thank you for giving me also the opportunity to visit this place. So what I'm going to talk about today is the work that I have done in the last 2 years, maybe last year, at Penn State in collaboration with Eugenio Bianchi. And also, there are some work in progress stuff that we're still working on. So I will spend like 3 or 4 slides giving you some very vague background and motivation, because I'm assuming that not everybody in the audience is familiar with loop quantum gravity. And the quantum information tools that I'm using are very basic, so for that I probably don't need many introductions. Then there will be a first part of the talk that will be on typical entropy, so we'll discuss page curve and its variance. And in the last part I'm going to introduce you the entropy and correlation in Bell network states in loop quantum gravity. So, yeah, the sacred graal in quantum gravity right now, in loop quantum gravity, is trying to find a class of states with correlation at space-like separation. Why so? Well, we all know that in quantum field theory, we have quantum field theory described by Fock space, states in quantum field theory, by Fock space. And the Fock space contains states with very specific short-range correlations, for example, Minkowski vacuum. And these states are fundamental to study the quantum nature of cosmological perturbation, for example, because we believe that the very, very early universe is described by a quantum state with highly entangled quantum state. And we also notice that there are no states in the Fock space with no space-like correlations. While on the other hand, in loop quantum gravity, the Hilbert space, over here, is a direct sum. Do not let me go into the detail on how this direct sum is defined. If you want, we can discuss later, over graphs, of a direct sum over some quantum numbers, spins, of a tensor product over the nodes of the graph, or of some Hilbert spaces. In loop quantum gravity, on the other hand, in contrast with quantum field theory, we have states with no space-like correlations. For example, spin networks that are states that are factorized in this Hilbert space. And what we're looking for are states with specific short-range correlations. And there are many proposals for them. And later I'm going to discuss one of them. So, let me give you a very qualitative and very artistic picture of the loop quantum gravity Hilbert space. So you take a graph, you assign the link of the graph SU2 quantum numbers, so just spins, and you assign to the node of the graphs intertwiners that are invariant tensor in the tensor product representation of the SU2 representation that goes into the nodes. So there's one intertwiner per node, one spin per link, and the Hilbert space is the direct sum over all the possible spins on the links of these invariant SU2 invariant spaces at the nodes. There's a very nice and there's a very nice picture for these Hilbert spaces that was proved or derived, or I don't know how to say it, 10 years ago. So you can think about these Hilbert spaces as Hilbert spaces of quantum polyhedra. So you can imagine a state in loop quantum gravity as a collection of quantum polyhedra glued together, but these quantum polyhedra are fuzzy, so they're do not have a well-defined shape. They have like superposition of quantum polyhedra. The only thing that that is well-defined is that shared faces do not need to have the same shape, but need to have the same area. That's the only requirement. Yeah. So that's basically the geometric picture of loop quantum gravity states. Imagine them as collection of quantum polyhedra. Each quantum polyhedra is a state, an element of this Hn Hilbert space. Okay. Why we think that information theory could give us very valuable tools to study quantum gravity problems. The things that we are interested in are correlations. So imagine that you have a graph, because I'm thinking about loop quantum gravity now. So take a graph, take a state in the Hilbert space at fixed graph, and take a subsystem. The subsystem is defined, for example, by selecting a region, so a collection of nodes. And in this subsystem, related to this subsystem, you have an algebra of observable, of operators. So you take two regions, A and B. You define the correlation between the two observables. Now, a very important result is that correlations of these two observables, or a combination of, is bounded by the entanglement entropy of the two region and the entanglement entropy of the region the union of the two region. That is usually called mutual information. Probably people from quantum information are very know.
Sorry, try not to raise your left arm because it's like rubbing
okay.
on the mic.
So people from quantum information are knows this quantity very well. This theorem was proved in 2008 by the group in Wien and Munich, I think. Okay. Notice that the left-hand side of this bound do not depend at all from the observable. So it's a quantity that you can compute directly from the knowledge of the state. So it's a property of the state. So given the state, you can compute this quantity, and you know that any two couple of observable, the correlation between these two are bounded in this way by this quantity. And so if you consider, for example, spin networks that are nothing but the tensor product of states at the nodes, of states of the Hilbert spaces at the nodes, these clearly have zero entanglement entropies because they are factorized. So for spin networks, there cannot be correlations of observables. On the other hand, another example of states without correlation are states that follows a volume law, or more in general, states for which the entanglement entropy depends on an extensive variable, so that basically the sum between the two entanglement entropies is exactly equal to the entanglement entropy of the union of the two regions. Therefore, these two terms cancels, and the correlation has to be zero. And at this point, we asked ourselves the question of what about a random state? So let me move to the first part of the talk. Yeah, sure.
Sorry, could I just ask, what is the meaning of the nodes and the vertices in that graph?
Yeah.
Like the physical interpretation.
Yeah, so, sorry. We should have stressed that. Oh, sorry, that way. Yeah, so you can imagine your SpaceTime to be foliated. So at each QISS, so at each slice, if you want a fixed time, you can imagine it as at the quantum level to be composed as grain of spaces. Each grain corresponds to one of these nodes. And each grain, if you want, you can pictorially imagine it as a quantum fuzzy polyhedra. So the nodes are grain of space. And the links tells you which grain of space is adjacent to which, and gives you, with the spins, the information about the area, so the size of that interface. Okay. Now I want to talk about typical entropy of a subsystem. So everything I'm going to tell you now is very general and works for any finite dimensional Hilbert space, any finite dimensional quantum system. But I'm going to do it with an example because it's simpler to describe. Okay, so for example, let's consider n spins. So I have a system of n spins that can be up and down. And let's consider as a subsystem a set of them, NA of them. So the full Hilbert space is nothing but a tensor product of C2 to the power n, so all the spins, and has dimension 2 to the power n. Okay. The subsystem is C2 to the power NA and dimension 2 to the power NA. Okay. Then I can define reduced density matrix by tracing out over the complement of the region A defined by the first NA spins. And I can compute entanglement entropy in the usual way. What we know is that the average entropy, by average I mean by picking a state that is random with a uniform distribution over the 2n spheres, n-dimensional complex spheres, sorry. What we know is that the average entropy over this random uniform distribution of states is close to maximal. And this is a famous result by Page in the 1995. In fact, you can draw what is usually called as Page curve, that is the amount of entanglement entropy as a function of dimension of the subsystem. So in this case, this is NA, and here I just drew an example with n equal 10, and this is NA that goes from 0 to 10. So it's close to maximal, but it's not maximal. The black line is the maximal amount.
Maximal, you mean the states that maximize it?
Sorry?
Is the value of on the states that maximize it? Maximal on the states?
No, it's maximal. It's NA log 2. So, yeah, so there are states that maximize, yeah, but that's the maximum amount of entanglement that you can get, yeah. Okay. So the average entropy is close to maximum. What we added last year, we computed also the variance, and we found out the variance is very small. So what you see here is concrete realization. So the blue line is the average, and the gray band is 3 sigmas. So it's 3 times the square root of the variance. And here, just for as an example, we picked out, like, we created 10 realization of this system. We computed entanglement entropy. So we took like 10 random states, computed entanglement entropy, and they all lie well inside this band. So let me give you a very brief.
That was for a fixed NA?
Sorry.
Subsystem?
So this is a function of NA.
It's a function of NA?
Yeah, this is NA 0. Of course, the entanglement entropy is 0. Then it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It's 0 then.
And for each NA, you chose randomly states to
For each NA, you choose, yeah, probably I need to specify this better. So the random state that you choose is not, of course, a random state in the subspace. It's a random state in the full Hilbert space. And that's pure. Once you compute the reduced density matrix, that's not pure anymore, so then you have a notion of entanglement entropy. If not, entanglement entropy is trivially zero. So if I pick a random state in the H restricted to in this subspace, then entanglement entropy is trivially zero because the state is pure. Okay, let me give you a short sketch of the proof. So we, in the construction we did, we proved again Page theorem for the 10th time probably in the literature. That's another slight variation. But with this slight variation, we have great improvement. In fact, we can generalize it to any momenta of the probability distribution of the entanglement entropy of the subsystem. So let me just give you 5 steps of the proof. So first of all, the thing that you compute is not directly entanglement entropy, but you compute trace of the average of the trace of the reduced density matrix to some arbitrary power. And you average over all the possible states in the big space, in the full space. And this has been proved in the 80s that can be reformulated as an average over the eigenvalues of the trace of the density matrix to the power r, that is this object here, with some specific measure that has been computed. Once you compute this object, that could be quite complex, but it's doable. You just take the limit r equal to 1 of the derivative with respect to r. And that's similar to the usual replica trick that you do when you study quantum field theory. What you get is an exact result. Meaning, by exact I mean that the result do not depend. So it's not an approximation. It holds for any dimension of space and subspace, where here dA is the dimension of the subspace and dB is the dimension of the complement. And these psi are derivative of the gamma function. What's interesting is that there's an asymptotic expansion that can be immediately derived when the complement is large. That tells you that the average entropy is log dA, that is the maximum amount, minus some quantity. So it's slightly smaller. Everywhere I will assume that A is the smaller of the two. If that's not the two, so A is the subsystem is smaller than the complement. If that's not true, then the two dimension switches. So to compute the variance, we use the same technique. We just have an object that is multiplicated. So you just compute the trace of rho a to some power, rho a to another power. Then you take double derivative, double limit, and what you obtain is just the average of the entropy squared. And by carrying out the complicated algebra, but it's just algebra, you get this result for the variance. And what we can see is that for large dimension of the complement, the variance is very small because it's 1 over the dimension of the complement. So from this, we are tempted to conclude that the average entropy is typical. So selecting or picking a random state, the average entropy characterize very well the entropy of that particular random state. And we compared also to, there are similar results in the literature. In particular, I'm referring to the result by Hayden and collaborators, 2006. Yes. 2006. But these results are on a concentration measure, so they speak about the cumulative probability, and the result is that the cumulative probability of finding a value for the entanglement entropy smaller of some number decays exponentially. And I plotted here in a specific realization what this bound is telling you. The orange dots are the actual realization, while the blue curve is an approximation that we are suggesting. So using the algorithm, the technique that we are suggesting, you can, in theory, compute all the moment of this probability distribution. And if you know all the moment, you could reconstruct the probability distribution itself. So any moment is computable. For example, we also have in the paper, we had an explicit value of skewness. It becomes very long and complicated, but we have it. What I want to stress is just, if you know just the average and the variance, the normal distribution is a good approximation already of this probability distribution, and gives you a better characterization of the Hayden result of this probability distribution, provided that this is a theorem. What we are suggesting is a qualitative, it's quantitative, but it's also qualitative description of the probability distribution, in the sense that we don't really have control on how well this is a good approximation. Okay. This is very interesting, but let me go very fast here, because I want also to say something about loop quantum gravity. The similar results holds also in the case of a presence of a center. So when your Hilbert space is not directly the tensor product of two Hilbert spaces, but it's a direct sum of tensor products. And the simplest example that we can think of, just take n spins and you put them in an external magnetic field, and you say that what you're interested in is not the full Hilbert space, but it's an Hilbert space with definite energy. So if you fix the total energy, then the structure of your Hilbert space is not anymore just the tensor product, but it's a sum over all the possible values of the energy in the subspace of tensor products. So for example, in the what I want to stress is that this is, if you want, a very simple model, very simple example, but there are some physical systems that still can be described with this very simple model. So it's not completely theoretical. What's interesting is that if you compute the average entropy, in this case, what you get is this expression that looks a lot like the thermal entropy for the subsystem with energy, the average energy. And in particular, what we can do is define some sort of notion of temperature from the entanglement by just taking derivative of this average entropy with respect to the average energy. And what we also derived is an estimate of the distance between the maximal entropy and the average entropy at half subsystem. But let me, and this is proportional to the heat capacity. This is an open problem in the field. But let me skip on this because of time. So also for typical entropy in the presence of a center, we have the exact formula for the average entropy and the variance, and still the average entropy is typical. That's the message that I want to pass. Okay, so entropy and correlation in Bell network states. As I hinted you before, we want to use information about entanglement entropy to bound correlations. And for random state, since the entanglement entropy is almost maximal, so follows a volume law, there are basically no correlations. So in loop quantum gravity, we need to find a specific class of states with desired properties to allow space-like correlations. And the idea is to define these Bell network states. How we define them? These are a class of states that are trying to glue the quantum polyhedra I was talking before with entanglement, meaning that we are trying to not only correlate the average shape of neighbors' faces of polyhedra, but also correlate fluctuations. And to do that, it's a complicated definition, but Lucas, that is here, is the expert, because he did that. Is to use squeezed vacuum techniques to correlate the shapes and their fluctuation link by link. To do that, you just enlarge the full Hilbert space and squeeze. This enlarged Hilbert space is related to the Hilbert spaces of oscillators, and you can squeeze them. These are all technical details, don't worry about that. And then you need to project that. And the final result is that you can define a class of states depending on one complex parameter per link that represent the average area of the on that link and the extrinsic curvature. And
excuse me. So these Hilbert spaces, are they finite dimensional?
yes, they're finite dimensional. Sorry.
On the previous slide, you have a sum in.
Let me be. Everything up here, everything is finite dimensional.
Okay.
Technically, this Hilbert space, this is infinite dimensional.
Okay, this is infinite.
This is infinite dimensional. Yeah. So, if I want to talk about typicality here, to have a well-defined notion of random state, I need a finite dimensional Hilbert space, because for infinite dimensional, how do you pick a random uniform distribution? Okay, so if you want to speak about typicality in this Hilbert space, you need to put some cutoff or derived probably from some physical condition, or I don't know, the condition that you prefer. But these states are defined for in the whole infinite dimensional Hilbert spaces. And what I want just to stress is that we computed a bound on the entanglement entropy for this class of state in the limit of large quantum numbers. Okay, let me just go back one step. So we computed actually bounds on, so this class of state is defined as a superposition over all the possible values of the labels, of the spins, of some other states. To compute the entanglement entropy of these, you just need to compute the weighted entanglement entropy of these states plus the Shannon entropy of the weights. So the Shannon entropy of the states of the weights are the easy part. The difficult part is compute the entanglement entropy of these states that are quite complicated. And that's what we did here. So we fixed the spins and we computed the entanglement entropy of a state that lives just on the tensor product of these node Hilbert spaces defined in this way. That is a piece, let's say a brick of the full Bell network state. And what we derived is a bound on the entanglement entropy for large spins. And we see that the entanglement entropy is bounded by the logarithm of the scaling parameter, the number of boundary links of the area, of the region, and two constants. And this constant depends on the region and on the graph. I don't have a closed formula for it, but I can operationally tell you how to compute it case by case. And we also did some numeric computation. If you are interested in the code, it's available here. By doing the numeric computation for very small graphs, unfortunately, because that's what we can explore with limited resources, and for large spins, we can compute the entanglement entropy of, for example, a single node, two nodes, and we can fit, we can fit this, this behavior with a logarithm, and we can compute the mutual information. And we see that for this class of state, correlation at increasing value of the rescaling parameters are allowed because this bound increase. While, for example, for random states, as I was telling you before, correlation are not allowed because they are power law suppressed. Okay, so let me conclude here.
Yeah.
I have 1 minute, I will just summarize.
Sure.
Okay. So what I showed you is that we have some very nice and interesting results about random states in finite dimensional Hilbert spaces. In particular, we found that random states have typical entropy. We made comparison with concentration of measure results. The correlation are vanishing. These results holds also in presence of a center. We have a notion of temperature for entanglement. This is very interesting from the prospect of deriving temperature of black holes, for example, where ensembles and usual quantum mechanics applies in a strange way. And we have a result for half volume correction, while for entanglement entropy of Bell network states, we derived an analytic asymptotic of the entanglement entropy. There is a sort of area law behavior, because it depends only on the number of boundary links of the region. We developed a numerical code to compute the entanglement entropy. And this class of state is a good candidate for a class of state that allows a non-vanishing intertwiner correlation, so non-vanishing space-like correlation. Well, thank you very much.
So we will take 2 questions. There are any?
Concerning the Bell network states, I mean, so far what we showed was kinematical. Can you say something about whether, for instance, I mean, the states can be obtained when you consider dynamics? Of course, at least graph non-changing, or I mean, a certain approximation. Do you have any hint about that?
No, in the following sense. So everything I told you about here, everything is kinematical. There's no dynamics anywhere, not even in the quantum information part. When I'm speaking about spins, I'm not assuming any Hamiltonian anything. I'm just describing the kinematical Hilbert space. How these states evolve, for example, I don't know. Under spin from evolution, for example, or I have no information about that.
But do you have any, I don't know, thoughts whether in bell network state can be associated with the ground states, for instance?
Oh, that's the hope. The hope is that since you can prescribe the correlation that you want, it's a huge class of states. The hope is to be able to, for example, reproduce the fall-off condition of Minkowski vacuum, and that's the final goal. Being able to have a state that represents, for example, Minkowski, Minkowski space-time.
But do you have any clue how to do a step towards this direction?
No. That's very complicated.
Yeah, that's why I'm asking.
Okay, thank you. So, another question?
Yeah, so these power network states, should I think of these as analogs of spin network states?
Okay, spin network states are a basis of this space that is factorized on nodes. Okay. So spin network state is a state in here with a prescribed spin for each link, a prescribed interpolation for each node. So it's completely factorized and has no, therefore it has no the entanglement entropy of any region is exactly 0 because the state is factorized. Well, these states here are a very precise and very selected superposition of spin network states, if you want. Such
very precise. You mean you have a particular?
Yeah, I have a prescription for constructor. This prescription is the following. This is a formula, but the idea is that I try to correlate a neighbor's quantum polyhedra in such a way the shape of the phase is in average correlated, and also the fluctuation of the shapes are correlated. While spin network states have quantum polyhedra at the nodes, they're completely uncorrelated. And not only the shape of the phase can be whatever, also the fluctuation are completely independent. The only thing that are the same is just the value of the area.
So what's the motivation for this prescription?
Yeah, finding a state with non-zero correlation. A class of states that allows non-zero correlations
But not to
of
be
operation.
accurate, right? Because
Sorry?
you want an area law, not a volume law. So not
Yes.
too many correlations.
Yes. These are link by link correlations. So they're like first neighbors in Sam's correlation. So they're short range correlation. And we expect that when you have short range correlation, you also have another behavior of entanglement entropy.
I have a short question.
Yes.
So, if I give you a discrete geometry, in the same way that we know with twisted geometries how to set up a state that is picked on it, we can do the same here. We can choose the lambda to match some discrete, some distributional piecewise flat geometry.
Yes.
Yes.
That's it. Yes.
Has anyone done that?
If you want, this is a generalization of a coherent state in some sense. So the coherent state just correlates the shape, the average of the shape. This also correlates fluctuations.
Okay. Okay, so let's take this figure again.